Hey everyone, welcome back to probability theory. This will be lecture 5 of the course, and in this section we're going to discuss counting methods. So let's go ahead and jump into that, and we'll call this section 1.5, counting methods. So what we're going to do here is we're going to kind of walk through some useful results from the field of mathematics known as combinatorics. So combinatorics. Okay, and so this is a huge branch of math, and we're just going to scratch the surface, borrow a couple of key results from combinatorics that we will need in order to solve serious probability theory problems. And so really the issue that we're butting up against is that sometimes the number of simple events in a sample space is very, very large, and enumerating them is very difficult, and if not impossible, without these kinds of advanced tools. And so we will be using combinatorics to help with examples where the sample space is very large. Right, and so we haven't really seen examples like this yet, but we'll get into a couple here where, without using these kinds of rules and these kinds of tools, we wouldn't be able to make any headway. And so the first principle that we're going to borrow from combinatorics is something called the MN rule. And I don't know if everybody calls it this, but the textbook that I'm using does, and so we'll go with that. I remember it being called that when I was an undergraduate. So the MN rule. Okay, and so this is a straightforward principle, but the idea is that given m elements, all right, we'll just call A1, A2, ... AM, so m of them. Given m elements and n elements, we'll call them B1, B2, Bn. It is possible to form m times n pairs containing one element from each group. Okay, so if you have m elements in group 1 and n elements in group 2, and you want to form pairs based on these two groups, the total number of pairs you can form is m times n. Right, and so like, for example, a pair would be if I choose A2 and I choose B5. Another pair would be A1 and B6, for example. Right, those are what we mean by pairs. Okay, and so let's see an example where this is useful, and then we'll talk about how this can be proven. So let's say we're given 2 die. Okay, given 2 die, how many distinct pairs can be rolled? How many distinct pairs can be rolled? Okay. Well, I mean, just using the MN rule, I got 6 options on the one die and I got 6 on the other, so 6 times 6 equals 36. But let's try to visualize this a little bit. So what I'm going to do is I'm going to draw a grid. So this vertical over here is going to represent roll number, well, say roll 2, and then this one is roll 1. It doesn't really matter. Okay, and so you can kind of think of this as a grid, right, where the intersection here, for example, would mean that I roll a 2 on the first, a 2 on the second, and a 2 on the first. Okay, and maybe this one over here represents a 5 on the first roll and a 4 on the second roll, right? So this is roll 1. Sorry about that. The top row is roll 1, and this is roll 2. Right, so if I roll a 5 and a 4, then I've got it captured here. And so you can see that I'm going to have the 1, 1, the 1, 2, the 1, 3, the 1, 4, the 1, 5, the 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and all of them are going to be, here's the 6, 6 down here. Right, and so obviously this is going to, the intersections on this grid is going to capture all of the different distinct pairs that can be rolled. And so we know that, you know, if I were to try to find the area of this grid, it would just be 6 times 6 equals 36. Okay, and so we can use this as kind of the blueprint for a sort of visual proof of the MN theorem, of the MN rule. Right, and you would just have to extend your grid to arbitrary dimension. So maybe I would say, so here's the kind of proof would be like A1, A2, dot, 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 AM, and then B1, B2, dot, 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 BN. Okay, and you can kind of think of it like this as a grid. Right, and so all of the entries of the grid are going to represent pairings. Right, so we've got a lot of dot, dot, dots here, right? Dun, 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 dun. But this would be A1, B1, A1, B2, A1, BN, right? A2, B1, A2, B2, A2, BN, AM, B1, AM, B2, AM, BN, right? And with a little bit of effort, you could easily convince yourself that this is indeed all of the possible pairings that you could get. Okay, this is all the possible combinations. And so then, of course, the area here is M times N, right? So this is kind of a little hand wavy, but like you can see the principle here, right? This is just M times N. I got M of these, I got N of those. All the possible combinations are just multiply them together. Okay. Let's take a look at another example using this. So if you recall previous theorem, or if you watched the previous videos, we previously looked at an example involving flipping a coin 3 times. So we previously looked at an example where we flipped a coin 3 times, right? And in that example, we said we derived the sample space kind of just by, we brute forced it out. We just figured out what they look like and kind of wrote them all out. And they look like this: H, 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 T, heads, 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 tails, heads, tail, heads, tail, heads, heads. And then we did from the other direction: tails, 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 heads, tails, heads, tails, and heads, tails, tails. Okay, so that's what we got last time when we looked at this problem in the previous example, in the previous lecture. Right, and so if you think about this, this is really, so each one of these objects in sample space is really selecting an element from a group of 2, right? So for example, H, 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 this first one was selected from H and T, a group of 2. The second element here, so there's like 3 spots here, the second spot was selected from, you know, N equals 2 objects. And the same thing for this third spot. We selected it from H and T. It just so happens we selected H each time, but this is just an extension of the MN rule, right? So we can extend the MN rule to just be two groups, like M times N, or maybe if it's 3, we can think of it as an M times N times P, whatever the letters you want to use are. But basically, that's what this is. So we're choosing one of them from 2, and then one of them from another 2, and then one of them from another 2. So this would be 2 times 2 times 2. That's the number of ways to choose 3 elements from 3 groups of 2. And so we got 8, right? And so you can just see that that aligns with what we did when we sort of brute forced the sample space from just reasoning about it. Okay, so it aligns with the previous result, and it's a nice way to kind of see that you can extend the MN rule to include more than just two groups. Okay, let's take a look at a kind of tricky example, actually. Let me make sure I don't have another easy example first, though. No. Okay, we're going to jump right to this trickier example, which is a good example. Let's say a bag contains 50 different numbered balls, right? And we'll just say they're numbered 1 to 50. Okay, so one of the balls just have a number on it. There's 50 of them. They all have a number 1 to 50. So they're distinctly numbered. Okay, we randomly draw 5 balls, one after another, with replacement. Okay. So what does that mean? This with replacement. So the idea is I've got, this bag, and in it there are 50 balls. I'm not going to draw 50, but you just assume that's 50, right? I take one out, I look at it, maybe I write it down, maybe it's a 10. And then what do? I throw it back in, right? And then I do the same thing again. I take another one out, I look at it, oh, maybe it's a 7, oh, and then I throw it back in. And then I do it again. I take one of the balls out, I look at it, oh, look, I got the 10 again. That can happen. I throw it back in, right? Because I'm replacing the balls as I take them. I take them out, I look at them, I throw them back in. So we'll frequently talk about with replacement and without replacement. And so this is a good example to introduce that concept. So with replacement means when you pull something, when you sample it, you put it back in afterwards. So it goes back into the possible balls to be selected. Okay. All right, so a bag contains 50 different numbered balls. We randomly draw 5 balls, one after another, with replacement. Okay, and the questions are, the first question we want to know is how many possible outcomes are there in this sample space? How many possible outcomes are there in the sample space? And then the second question is, what is the probability that all 5 balls drawn have different numbers? That all 5 balls drawn have different numbers. Okay, all right, so these are 2 tricky problems, right? So I got 50 balls in this thing. I'm drawing them out 5 consecutively and replacing them each time. And so first question is, how many possible ways are there to do that? And then secondarily, what is the probability that all 5 balls drawn have different numbers? Okay, so let's think about what a simple event looks like here. So I draw out a ball and I write down the number and I put it back, and I draw another ball and I write out the number and I put it back, and I draw a third, look at it, throw it back in, a fourth, look at it, throw it back in, and a fifth, and look at it and throw it back in. Right? So this basically a 5 tuple between 1 and 50. These are the simple events. So the simple events are a 5 tuple with entries between 1 and 50, right? And it's possible, one of the entries in there is 1, 1, 1, 1, 1. It is possible to draw the same number 5 times in a row. It's also possible to, go 1, 10, 17, 1, 26. That would be another one, right? Then, of course, 50, 50, 50, 50, 50. That's one. You could get lucky and pull 1, 2, 3, 4, 5. You know, that's a possible entry. So these are all examples that are in the sample space. Now the question is, how many of these examples are there? Okay, so how many possible combinations are there? Well, this is really an extension of the MN rule, right? So we're really drawing 5 times from a group of how many? Of how many different objects? 50. So we're drawing 5 times from a group from groups of 50. So really, it's just 50. I got 50 options for the first one. Times 50, I got 50 options for the second one. So this is like my M, my N, and then another one, another one, another one. So it's really 50 times 50 times 50 times 50 times 50. Otherwise known as 50 to the 5th power. And so what is 50 to the 5th power? Well, this is a big number. This is 312,500,000. So this is how many combinations like this is possible to get. Okay. All right, so that answers part 1, right? And you can see this is just an extension of the MN rule. Just kind of thinking of, you know, each one of these. This is drawn from a group of 50. This is drawn from a group of 50, from a group of 50, from a group of 50, from a group of 50. All right, just so happens that the M's and the N's and whatnot are all the same size. Okay, so there's a lot of possible outcomes. 312 million of them in particular. Okay, so then part 2 asks, what is the probability that all 5 draws have different numbers? Now, there are a lot of ways that this can happen as well. All right, so let me put a new sheet here. So, what is the probability that all 5 draws have different numbers? What is the probability that all 5 draws are different numbers? Well, I mean, just kind of thinking about this is probably likely to happen, isn't it? Right? And really, when I think about the probability of this, it's going to be, I mean, the denominator is going to be 312,500,000. And the numerator really needs to be the number of ways that this is possible. Okay, so how do we count the number of ways to do 5 consecutive draws with replacement without getting the same number twice? Well, we just have to visualize this, okay? So let's think about it like this. Draw 1. Well, I've got 50 options, right? Okay, so I've got 50 possibilities, numbers 1 through 50. Okay, what about draw 2? Well, I don't have 50 possibilities anymore, right? Because I actually got something on the first draw. I put that ball back in, so it's in play, but I don't want to consider that. So instead of 50 possibilities, I have 49 possibilities. What about draw 3? Well, now I've already drawn 2 balls that are distinct, so I only have 48 remaining that are different, right? So 48 possibilities. About draw 4, 47 possibilities. And draw 6, right? There's only 46 balls in there that haven't been yet drawn, right? So I have to draw one of those 46. Right, so this is again an MN kind of problem. This is the first group, this is the second group, the third group, the fourth group, the fifth group. Right, so I got 50 here, I've got 49 here, 48 here, 47, 46. And so really the number of ways to draw combinations that are all 5 distinct would be the product of all of these things, just the MN rule. So 50 times 49 times 48 times 47 times 46. Now, if you do that math, you'll find that this is 254,251,200. There are 254 million ways to do this. Right, and so obviously you can see with these examples, if we didn't have these tools of combinatorics, there's just no way to solve this problem. If you had to actually exhaustively write out all the possible 5 tuples, you just never could do it. I mean, maybe if you had a computer you could do it, but you can't do it certainly by hand, right? And so what's the probability then that all 5 draws are different? All 5 draws are different. What is that probability? Well, just to kind of lay this out and make sure it's kind of crystal clear, this is the number of sample points with no repeat numbers. It's the number of sample points with no repeat numbers divided by what? Well, the total number of sample points. Right, and what is that? Well, we just found those numbers. 254, 251, 200 over 312, 500, 000. If you do that math, you'll find this is about 0.81 or 81%. Okay, so about 80% chance that you're going to draw 5 numbers that are not the same. Perfect. So it's a little trickier example, but it kind of illustrates the power of these tools. All right, let's move on to the next idea. So I've got a definition here. And this is going to be the definition of what is called a permutation. So an ordered arrangement of R distinct objects is called permutation. Okay. So an ordered arrangement of R distinct objects is called a permutation. Okay. And we'll say the number of ways of ordering n distinct objects taken R at a time, is denoted by P and R. Okay, so this is the notation we'll use. Okay, so a permutation, you can think of it like, strings like this, strings of numbers or characters. A, B, C, D, E, where the order matters, right? The order matters. That's why it says ordered here in the definition. So for example, A, B, C, D, E is distinct from B, A, C, D, E, even though these two permutations contain the same elements, namely A, B, C, D, E. Because they're in a different order, we think of them as distinct. Now this is a kind of a subtle point, but make sure you understand it. Order matters. If order matters, then the number of permutations goes up pretty dramatically, right? Just think about that for a second. All of the different ways to permute these 5 different things. In the case of permutations, if order matters, that tends to make the number of possibilities kind of grow. Okay, and so the previous example with the 5 balls out of 50, those were examples of permutations, right? They weren't. They were they were all different, right? And order mattered. The order in which they pulled out is how we enumerated them. So, so these are called permutations. Now, the further question would be like, how do we know what this number is, this PNR? This is n objects permuted r at a time. So what is this number? Well, that's the subject of our next theorem. So PNR is equal to n times n minus 1 times n minus 2 dot 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 n minus r plus 1. Okay. Now, the proof of this is really just an extension of the MN rule. So let's kind of talk through this proof. So this is an extension of the MN rule. Okay, so the number of ways of choosing item 1. How many is there? Well, there's n ways to choose item 1. Okay. Now remember, they're distinct, right? N distinct objects. And so what are the number of ways of choosing item 2? Well, it's n minus 1, right? And item 3, that's n minus 2. Dot, dot, dot. Remember, we're choosing r items in total. So the number of ways of choosing item r is going to just kind of look at the pattern. Item 2 is n minus 1. Item 3 is n minus 2. So item r is n minus r plus 1. Okay, and so this is group 1, this is group 2, group 3, group 4, right? So PNR is just equal to the product of this. That's the MN rule side of things. So n times n minus 1 times n minus 2 dot 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 n minus r plus 1. Okay. And so this is what PNR is. Now in practice, we actually use a different formulation, it's a much more convenient formulation than this. And what we'll typically do, what we'll typically write instead is that this is equal to n factorial over n minus r factorial. Okay. It's easier to prove this using the MN rule if you kind of approach it from this standpoint, but then what we have to do further is we really want to show that this is equal to this, because throughout our use of this, we'll almost always rely on this formulation here in actually calculating that number. So how do we get from here to here? Well, let's do that quick. Okay, so note, what we're trying to show here is that PNR is equal to n factorial over n minus r factorial, which is just n times n minus 1 times n minus 2 dot 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 n minus r plus 1. Okay, so we've already kind of got to this piece of it just using the MN rule, but then how do we show that that's equal to this? Well, let's start with this n factorial over n minus r factorial. What is that? So these factorials, I assume people know what this is, but if you don't, this is a simple thing. N factorial just means it's just the product of n, of the integer n, and then all of the integers less than, all of the positive integers less than it. So it'd be n times n minus 1 times n minus 2 dot 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 times 2 times 1, right? So all the way down. Okay. So that's just what n factorial is. We'll just put that there for a second, just in case we've never seen that before. Okay. And so let's think about this ratio here. What is n factorial over n minus r factorial? Well, let's take a second and think about what n minus r factorial is. So let's instead of r, let's put in like a number. Let's say n minus 2 factorial. Well, that's equal to n times n minus 1. Oh, sorry. That's equal to n minus 2 times n minus 3 times n minus 4, all the way down to 2 times 1. Okay, so again, it's just whatever integer this is, it's the product of all of the positive integers that are less than that number, less than or equal to that number. Okay. Okay, so then what is n factorial over n minus r factorial? Okay, well, let's think about let's just lay these out. So the top one would be n times n minus 1 times n minus 2, dot, dot, dot. And I'm going to put some middle terms in here. You're also going to have n minus r plus 1. You're going to have n minus r. You're going to have n minus r minus 1, dot, dot, dot. And you're going to go down to 2, and then finally 1. Right? So that's the numerator. It's just n and then everything between n and 1, all in the product. Then what is that denominator? Well, the denominator is n minus r times n minus r minus 1 times n minus r minus 2, dot, 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 all the way down to 2, all the way down to 1. Right? And so you can see why I included the middle terms here. So obviously, lots of this is going to cancel, right? So the 1's cancel, the 2's cancel, the 3's would be there and they'd cancel. The n minus r minus 2's are there and they cancel. N minus r minus 1 cancels, n minus r cancels. Right? And so you can see that this is really just n minus 1, n minus 2, all the way down to n minus r plus 1, which we just said was equal to Pn r. Okay, so that's kind of the simple proof. All right, so it's really just the mn rule extended, and then we want to write it in this notation here in this form for convenience sake. All right. Very good. Let's do another example. Let's do an example using this permutation idea. So here's an example. 3 names are to be drawn randomly from a bowl without replacement containing 30 names. So 3 names are to be drawn randomly from a bowl of 30 names, and we'll say without replacement. Okay. Now let's a cash prize of $100 goes to the first name, $50 to the second name, and $25 to the third name. So a cash prize of $100 goes to name 1, $50 goes to name 2, and 25 goes to name 3. Okay. How many sample points are associated with this experiment? How many sample points are associated with this experiment? Okay, all right, so that was kind of a little bit of a wind-up. But basically, I got 30 names in a bowl. I'm going to draw 3 of them out without replacement. I'm going to draw the first name, and that person gets $100. I'm going to draw a name from the remaining 29, and that person gets $50. And then there's 28 names left in the bowl. I'm going to draw 1 more out, and that person gets 25. The question is just how many sample points are associated with this experiment, i.e., how many different ways are there to draw 30 names from a bowl without replacement? Now, it's kind of, maybe it's obvious, hopefully it is, because the prizes are different, the order matters, right? This is a permutation problem, therefore. So we're basically looking for 3 perms from 30, right? So what we're really interested in finding here is P33, right? And so this would be, we just know the formula from up above. This is 30 factorial over 30 minus 3 factorial. So n factorial over n minus r factorial. Okay, and so we know that that's equal to 30 factorial over 27 factorial. Now, these are huge numbers. You can possibly plug these into a calculator, but it's also very easy to simplify these most of the time. All right, so let's just start over here. I got P30 over 3, which we said is 30 factorial over 27 factorial. Right, so this is 30 minus 3 is 27. And so if you just kind of visualize, this is 30 times 29 times 28 times 27 times dot 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 times 2 times 1. That's the numerator. And the denominator is 27 times 26 dot 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 times 2 times 1. Right? And so you can see that all of these are going to cancel. And so what you're left with is really just 30 times 29 times 28. Okay. And you can do that math. You can multiply those together, and you'll see that there are 24,360 ways to choose 3 names from 30. So this numbers just explode very quickly, right? You think, wow, it's just 3 names out of 30, but boy, there's 24,360 different ways to do that. Okay. Very good. Another example. In this example, we've got a classroom with 8 students. And the professor wants to select 3 of them to give presentations. First, second, and third in that order. Right? So a class has 8 students. And the professor wants to select 3 of them. 3 of them to give presentations. First, second, third, right? So, they have to go in that order. So the first person selected out of, the 8 has to go first, and then second, and then third. Okay. So 2 questions here. How many possible ordered arrangements are there? How many possible permutations are there? And then secondarily, what is the probability that Alice goes first? Right, so a girl named Alice. Let's just assume everybody in the class has a different name. So what is the probability that this individual person, Alice, goes first? Well, the answer to the first question is straightforward. It's P83, right? I've got 8 students. I'm going to do 3 permutations of those 8 students, right? So that's just 8 factorial over 8 minus 3 factorial. So 8 factorial over 5 factorial. And so I know that the 5, 4, 3, 2, and 1 will all cancel, and this is just equal to 8 times 7 times 6. Right? And we can multiply that together, and we'll see that that's 336. Okay, so there's 336 different 3 perms just from 8 students. Okay. Now for part 2, what we're interested in knowing is what's the probability that Alice goes first? Okay, and so the way to think about this is you've got 3 choices. You've got the first person, the second person, and the third person. So if Alice goes first, that means this is Alice, for sure. Right? And then you've got number 2 and number 3. Okay, and so how many choices are there to put Alice first? Well, there's just one way that can happen, one choice. What about the remaining 7 people, right? They're not Alice. There's only 7 other people, and none of them are Alice, right? So there's 7 choices here. And then that person gets chosen. How many choices are there here? 6, right? Okay. And so how many ways are there for Alice to go first? Well, there's 1. This is the MN rule. 1 times 7 times 6. 1 here, 7 times 6. So it's triple. Multiply them together. 42 ways. All right, so then the probability that Alice goes first is equal to 42 over 336, which, if you do that math, you'll see is 1 over 8. Now, hopefully you're thinking to yourself, hold on, isn't there an easier way to answer that question? Yes, indeed. There is an easier way to answer that question. You could just kind of look up here and say, I got 8 students. We're going to randomly draw the first presentation out of the entire 8 students. You know, Alice's name is in the hat. It's 1 of 8. So 1 out of 8 is the probability that Alice will be chosen first. Okay, and so kind of a different way to approach that same problem, but then intuitively you could just say, well, there's 8 students in the hat. She's one of them. The probability of her coming out of the hat first is 1 in 8. Very good. Okay, so different ways to kind of get to that same answer. All right. Next up, we've got another theorem, another counting method. Okay, so this theorem says the number of ways of partitioning n distinct objects into k distinct groups containing n1 in the first group, n2 in the second group, and so on, and k in the kth group is, and we denote it like this, n, and then you've got an n1, n2, ... nk, and it's kind of in these weird in these sort of parentheses here, but there's no bar between. This isn't a fraction, and this isn't a product either. This is just kind of a spatial arrangement here. But so the number of ways of partitioning n distinct objects, that's the n distinct objects, into k distinct groups containing this many, this many, this many, n1, n2, nk is this. And what this means in factorial notation is just n factorial divided by n1 factorial times n2 factorial times nk factorial. Okay, and so you may be wondering, like, okay, hold on, what is this about? Let's do an example where we're going to kind of take this structure and break it apart. This is extremely useful little theorem. And so here's an example of where this comes into play. I've got 9 district students, right? 9 district students, and they must be assigned to 3 project teams. Must be assigned to 3 project teams. Now, Team A has 4 spots. Team B has 3 spots. And Team C has 2 spots. Right, so I got 9 students, and I want to distribute them to these 3 teams. 4, 5, 6, 7, 8, 9. There's 9 spots total, 9 students. Everybody's going to some team. But I've got 4 spots on Team A, 3 spots on Team B, 2 spots on Team C. So I'm partitioning these 9 students into these 3 teams, right? And they have different sizes, the teams. Okay, and so 2 questions. The first question is, how many assignments are possible? Well, let's start with that one, and then I'll introduce the second question. So the first question is just how many assignments are possible? Well, this is a straight example of the theorem we just talked to. The number of ways of partitioning n distinct objects, like 9 district students, into k distinct groups, i.e. 3 project teams, containing n1, n2, nk elements respectively. A has 4 spots, B has 3 spots, C has 2 spots, is just this formula right here. And so this is n n1, n2, n3. Okay, and so the n here is the 9. n1, n2, n3 is the number of spots respectively. So 9, and then 4, 3, and 2. Right, this is the sort of notation we use to denote this number. But then how do we calculate it? Well, it's 9 factorial divided by 4 factorial times 3 factorial times 2 factorial. All right, that's fairly easy. That's an easy thing to set up. Now let's go ahead and simplify this. Right, we can actually calculate what the number is. So that numerator is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now we're going to talk through this and how to make this a little bit simpler. The bottom is 4, 3, 2, 1, right? 4 times 3 times 2 times 1. And times, so there's that one. And then you've got 3 times 2 times 1. Some people say you don't include the 1. Some people say you do. But you can obviously tell it doesn't matter. And then 2 factorial is just 2 times 1. Okay, now notice something that happens here when you have a factorial divided by another factorial that's smaller, right? Obviously, all of these are going to cancel, right? So you could basically write this up here as 9 times 8 times 7 times 6 times 5, right off the bat, because these will cancel, right? And so you're just left with 9, 8, 7, 6, 5. So whatever the largest number that you're dividing by down here, you can just take that out of the factorial immediately. Right, but then notice that other things will cancel here as well, right? So the 6 will cancel with the 3 and 2, right? And then the 8 will cancel with the 2, and you have a 4, right? So this is really just like 9 times 4 times 7 times 5, okay? And when you multiply all that together, you should get 1,260. Okay, so that you've got these 9 students. They must be assigned to 3 project teams. So the total number of distinct ways to do that would be 1,260. Okay, you can kind of think of this as a 9 permutation. So you basically have 4 spots up front here, and that's team A. And then followed by 3 spots here, which is team B, followed by 2 spots down here, which is C. Sorry about that. So you got this kind of 9 permutation here. Okay, all right. Very good. Let's talk about the second part of the problem now. So the second part of the problem asks, what is the probability that Alice, Bob, and Carol are on the same team? Okay, what's the probability that Alice, Bob, and Carol are all on the same team? Now we got to think about this logically, and we got to kind of break this apart. So they can only all fit together on team A or team B. So remember, A has 4 people, B has 3 people, C has 2 people. If they're all on the same team, they're going to have to be on team A or team B. All right, so let's think about team A first. So team A has 4 people. 3 of them are selected, Alice, Bob, and Carol. So you got 1 person remaining on team 6. So we basically need to choose 1 from 6 for the remaining slot. Right, so let's kind of visualize this. I got 4 slots. I got Alice here, I got Bob here, and I got Carol there, and I got 6 options for this guy. Okay. All right, and so if Bob and Carol and Alice are all on team A, we basically choose the 1 remaining member from the 6 people, and then we'll split the remaining 5 into B3. And so into teams B and team C. So I choose 1 person here, and I have 5 left to break between team B and team C. So 5, 3, 2. which is 5 factorial over 3 factorial times 2 factorial. And that, of course, is 5 times 4, and then canceling with the 3 factorial here. And then I've got 2 times 1, so that's really 10, right? 5 times 4 is 20, divided by 2 is 10. So there's 10 ways to break up the remaining 5, and I got 6 options here. So total is 6 times 10. 60 ways that Alice, Bob, and Carol could all be on team A. Right? There's 60 ways that they could all land on that team. Now, what if they're all on team B? What if they're all on team B? Well, if they're all on team B, there's only 3 spots on team B. That means team B is full, right? Team B is full if Alice, Bob, and Carol are on it. So the remaining 6 people have to go onto team A and team C. So the remaining 6 people are split into team A and C, right? And so we know how to do that. That's just 6, 4, 2, which is 6 factorial over 4 factorial times 2 factorial. And so this is just 6 times 5 over 2 times 1, and so that's 15. So there's 15 ways that Alice, Bob, and Carol can be on team B. So the probability that Alice, Bob, and Carol are on the same team, the numerator there has to be all the ways that they could be on team A plus all the ways they can be on team B. So you got 60 plus 15. Okay? That's the numerator, and so that's 75. Okay, so the probability then that they're on the same team is going to be that number divided by the total, the total, all of the different ways that, the teams can be divided up. So remember, the probability Alice, Bob, and Carol on the same team, that's equal to this 75 divided by what was the total number of simple elements in the sample space? Well, it was like 1,260, right? All right, and so when we do that math, that's 0.0595, so basically about 6% chance that they're all on the same team. Okay, very good. Very good. So there's a 6% chance that Alice and Bob are on the same team, and that is what we see here. All right, so we've got one more combinatorics rule that we need, right? And that one I'm going to motivate with an example here. All right, and I'll just preface it by saying that in many cases, the order of the array is not important. So in many cases, the order of the array is not important. Right? And we've just been looking at how the order of the array actually is important, but in some cases it's not. And here's an example where the order doesn't matter. Here's an example where the order doesn't matter. An employer wishes to select 2 applicants for a job out of 5 possible applicants. An employer wishes to select 2 applicants for a job out of 5 possible applicants. Okay, and so, this is a simple example where it's like, I've got 5 applicants, I'm going to randomly grab 2 of them to interview or to give the job to or whatever. Right? It doesn't matter the first one I pull versus the second one I pull. I pull 2, and those 2 are getting the same treatment afterwards. Okay, so in this example, it does not matter who is selected first and who is selected second. So examples of what's in the sample space would be applicant 4 gets chosen and applicant 2 gets chosen. Right? And this would be the same as, applicant 2 gets chosen, applicant 4 gets chosen. These are the same. The order doesn't matter. If these were permutations, right, if the first name chosen and the second name chosen got treated differently somehow, like maybe the first one got preferential treatment, then order would matter. But this example says he just wishes to select 2 applicants for a job out of 5 possible applicants. There's no indication that the order matters, and so these would be treated as the same sample. Sorry, as the same sample point. Okay. All right. And so in these cases, we'd say applicant 4 and 2 being selected is equivalent to applicant 2, 4 being selected. Right. And this leads us to the next definition. And that's the definition of a combination. So we say the number of combinations of n objects taken r at a time is the number of subsets of size r number of subsets of size r that can be formed from the n objects. Okay. Okay, so the number of combinations of n objects taken r at a time is the number of subsets of size r that can be formed from the n objects. Right, so if I have 5 applicants, 1, 2, 3, 4, 5, right, in my set, and I want to choose 2 of them, and order doesn't matter, that's just equivalent to me just identifying a subset. You know, maybe I select 2 and 4, or maybe I select 3 and 1, or 2 and 5, or 4 and 5, or whatever. But you see how you can kind of shift your thinking to, instead of thinking of these as combinations or tuples, ordered pairs, ordered triples, whatever, you can just think of them as subsets, right? So now we're talking about subsets. Okay. We denote this number. By, there's 2 ways to denote it. There's CNR like this, or you can denote it like this, NR like this. And so this is more common, I would say, and this is the one we'll kind of be using, is this NR notation. And we will frequently just kind of refer to this as N choose R, right? And so I don't know that it's necessarily called the choose function or anything like that, but it does, we do refer to it as n choose r. So for the example of the employer, it'd be 5 choose 2. Okay, and so then we can couple this with a theorem where we say that n choose r, otherwise known as CNR, is equal to PNR divided by r factorial, right? And more simply, you can think of this as n factorial over r factorial times n minus r factorial, right? So this will be kind of the way we want to calculate this. Okay, so n choose r is equal to n factorial divided by r factorial times n minus r factorial. Okay. Now we can very easily prove this, especially given the things that we already have looked at, right? And the proof is straightforward. It basically says selecting r objects from n objects is equivalent to partitioning the n objects into 2 groups, right? So selecting r objects from n objects, right? This is equivalent to partitioning the n objects into 2 groups. And what are those groups? Well, there's the chosen group, namely the R, and there's the unchosen group, or the not chosen group, we'll say. The not chosen group. That's the n minus r. Okay. And so this really, if you think about it, is just a special case of the previous theorem. All right, so this is just a special case of the previous theorem, right? And so we can kind of think of it like this. N choose r is equal to, it's equivalent to n r n minus r, right? Remember that, which we know is n factorial over r factorial, n minus r factorial. Okay, and it occurs to me we did not prove this. But you can go find the proof. It's all over the place. It's very common. It's a very straightforward proof, actually. Very intuitive. Okay, but if you go and find the proof, you'll have that proof. And this, you can see, is just a special case. You've got n total objects, and you're partitioning them into two groups, namely the chosen group, the r that you're choosing, n choose r, and then the unchosen group, the not chosen group, that's the remaining piece, the n minus r. Right? And so if you think about the problem in that arrangement, you'll realize that n choose r is just a special case of this bigger theorem here, this partitioning theorem. Okay. Very good. Let's do, I have two more examples I want to do quick. And so the first one is this. Okay, the first one is, let's do the first one. Let's let A be the event that exactly one of the two best applicants from the 5 appears in a selection of 2. Okay, previous example. Right, so that's the employer who wants to select 2 employees from 5. And so here what we're doing is we're going to say, let A be the event that exactly one of the 2 best applicants appears in a selection of 2. Okay, out of 5. All right, so again, back to that employer example. An employer is going to select 2 applicants randomly from a pool of 5, and we're going to let A be the event that one of those 2 that is selected is one of the best 2 applicants. Okay, so you got 5 applicants, 2 of them are the best 2, and you're going to randomly select 2, and A is the event that one of those 2 that you select is one of the best 2 applicants. Okay, so we want to find the number of sample points in A. And the probability of A. Okay. So we need the number of sample points in A and the probability of A. Okay, and so let's say that A, this is the size of A, this is the number of sample points in A. This is the number of ways one of the 2 best applicants can be chosen. From a pool of 5 in a sample of 2. Okay, so that's what we're after. What's that number? Let's see here. Well, this is going to be an MN problem, isn't it? All right, so we'll say the M here is, I've got 2 best applicants in my group of 5, and I want to choose one of them. So M is just 2 choose 1, right? And that's just 2 factorial over 1 factorial times 1 factorial, which is 2. Okay. I've got 2 best applicants. I just want to select one of them to be in my sample of 2, right? And so there's 2 of them. I've got 2 ways to select one of them, right? Okay. And I'm going to multiply this times my n group, which is, I've got the remaining applicant. I'm going to select 2 from the 5, and I've just selected 1. He's one of my best. And then the other one has to be one of the 3 lower ranking applicants. And that's my n. So n is 3 choose 1. That's 3 factorial divided by 1 factorial times 2 factorial, right? And so that's obviously equal to 3. So the number of ways to choose one of your best 2 is 2, and the number of ways to choose one of your worst 3 is 3, right? And so the MN rule says that the number of ways to have one of your best 2 applicants in your selection is 6. Okay, so by the MN rule, there are 6 sample points in event A. 6 ways to have exactly one of your best 2 applicants in your selection of 2 from 5. Okay. Now, we already found previously that there are 10 total ways to select 2 applicants, right? So, and there's 6 ways to select exactly one of your best 2 to be in there, right? So the probability of A, therefore, is 6 over 10, and so 60%. So I've got a 60% chance. So if I've got 5 total applicants in the pool, and 2 of them are the best 2, obviously, and I want to just select 2 randomly, the probability that one of the 2 that I select will be in the top 2 is 60%. Okay. Alrighty. And we'll say we have one more example. Just one more. I just want to kind of drive this home. That was a tricky example. Let's try this one. A club has 10 members. A club has 10 members. A 3-person committee. A 3-person committee is formed at random. The 3-person committee is formed at random. What is the probability that Alice is chosen to be on the committee? What is the probability that Alice is chosen to be on the committee? All right. Well, let's first figure out the total number of ways to select 3 from 10. Now here, order doesn't matter. You don't get special status if you're the first out of 10 to be chosen. Top 3 are chosen, and they're all in the committee. So order doesn't matter. This is a combination question. So 10 choose 3. Right, and that's 10 factorial over 3 factorial times 10 minus 3 factorial, which is 7 factorial. Okay, and so I can see that the 10 factorial and the 7 factorial are going to have a lot of interaction. So on the top, I'm going to have 10 times 9 times 8, and on the bottom, I'm going to have 3 times 2 times 1. Okay. And of course, a lot of stuff will cancel here. The 2 will cancel with that, and you get a 4. The 3 will cancel with the 9, you get a 3. And so this is like 10 times 3 is 30 times 4. And so this is 120. There's 120 possible committees that you could randomly select from the 10 members. Okay. Now, the number of ways to have Alice on the committee means that one of those slots automatically goes to Alice. Okay. So the number of ways to have Alice on the committee means one slot goes automatically to Alice. Okay, so one slot goes automatically to Alex. So we're going to fix Alice as a member, and we're going to choose 2 more from the remaining 9, right? And so that means I've got 9, choose 2, instead of 10, choose 3, right? And so we know that's 9 factorial over 2 factorial times 7 factorial. And so that means I've got 9 times 8 up top, and then 2 times 1 on the bottom. And so the 2 cancels, and this is 36. So there's 36 possible 9 choose 2 committees, because really Alice is already on the committee, so there's no reason to even count. There's no reason to even think you're selecting 3 from 10. One's already selected. You're really selecting 2 from 9. Okay, and so the probability that Alice is chosen is just 36 divided by the 3 choose 10 number, which was 120. Right, and if you do that, that's about what, 3 and 10, so that's 30%. Right, so there's a 30% chance. The number of ways to have Alice on the committee is 36, so the probability that Alice is chosen is 30%. So that is the probability that Alice is chosen to be on the committee. Okay, very good. So that's where we'll end this one. I know that's a lot of material, right? But hopefully you've kind of got the key pieces. You know, you've got the MN principle. You've got PNR principle. You've got NR1 ... RK, and you've got the N choose R. Okay, so these are really the 4 key counting devices that we need to have in place as we go forward. They'll be used not every day, but pretty much every day. I mean, in general, we'll use them a lot. So they'll be very steadily used throughout the rest of the course. So make sure you understand those. Spend a little time. Dig into the textbooks. If you've gotten a hold of the Wackerly book, I would get it. It's got lots. I mean, like so many examples, you can't even believe it. Hundreds of examples. So work through those, and you can easily pick these up. So, all right. Until then, take care, and we'll talk to you again next time. Take care.